lesson. Today we are going to be learning about introduction to linear and non-linear differential equations. Now, in the last class, I said that we are going to learn about formation of differential equations, but I'm sorry. Before we enter formation of differential equations, it is very important for you to understand how to identify linear and non-linear differential equations. So we're going to be looking at the conditions for linearity of differential equations. Now there are at least three main conditions that you should be able to use to discuss or predict the linearity of a differential equation. So the first one is that the highest degree of any derivative in the differential equation must be 1 or unity. So any derivative that is present in that differential equations, it must have a power or a degree of 1. So anything other than 1, it is no more linear again. Is that okay? Now I'm going to see with some examples later on. The second condition is that there must be no sine, no cosine, no tangent, no log, no exponential, no hyperbolic sine or cosine or tangent of the dependent variable. Now your dependent variable, I hope you'll still remember how to discover the dependent variable. If you don't remember, check up in my previous videos on how to find the dependent variable in a particular differential equation. So they're trying to tell us that there must be no sine, no cosine, no tangent, etc., any kind of function of any of the dependent variable. It must not be there. But if peradventure you discover a sine, a cosine, or a tangent of any of the dependent variable, then this is no more a linear differential equation. It becomes non-linear differential equation. Then finally, thirdly, and the last one is that the highest degree of the dependent variable must be 1 or unity. So your dependent variable too must have a power of 1. Anything other than 1, then it is no more linear differential equation. So briefly, we are going to be seeing some examples, some advanced examples, so to say, of how to classify differential equation according to the degree, the order, the type, the linearity, and so on and so forth. Ordinary differential equations. Okay. So let's look at a couple of examples. So example 1. So example 1 says we should test the order, degree, the type. I'm going to test the dependent variable. I'm going to check the independent variable. I'm going to check the linearity, okay, of the differential equation below. So the differential equation is d3y by dy cube by dx cube is equal to 1 plus dy by dx all squared raised to the power of 3 over 4. So solution. So the first question I have to ask you is, what is the order of this differential equation, and what is the degree of this differential equation? Now this kind of differential equations, or this kind of problems, are usually tricky because you need to observe this particular right hand side. So observe the right hand side. You can see that the right hand side is raised to 3 over 4th power. Now you have to modify this particular differential equation before you begin your solution. So the way we are going to modify it is we are going to take the 4th power of both sides. Okay, so take the 4th power of both sides. So when we take the 4th power of both sides, we now have d3y by the x cube all raised to the power of 4 is equal to 1 plus dy by dx all squared all cube. Alright, so you just permit me to squeeze in what the question wants us to write. So the degree of this particular differential equation, the degree, or first of all, let's start with the order. So the order is, it's actually, is it first, second, or third? So sorry, that's my mistake. So this is a third order differential equation. Remember, we said that the order of the differential equation tells us the highest derivative, okay, present in that differential equation. That's the highest position of the highest derivative. Okay, so we have third order. Then the degree, initially, if we hadn't taken the fourth power of both sides, someone would have been tempted to say that the degree of the differential equation is 1. But you can see now that after taking the fourth power of both sides, we see that the degree of this particular equation, which corresponds to the degree of the highest derivative, is actually 4. So this is a fourth degree differential equation. So we are looking at the type. So the type of this differential equation is actually what? Yes, ordinary differential equation. Okay, this is an ordinary differential equation. There is no partial differential equation parameter here. Then going to the dependent variable, so the dv, dependent variable, as you can see, is x. That is that variable on the denominator of your derivative term. So the independent variable, the idv, is y. Okay, so y is the variable of interest here, so it's actually on the numerator, so it's the independent variable. So we are going to test the linearity. So for the linearity, is this differential equation linear or not linear? So let's examine closely this differential equation over here. So let's examine and see whether it is linear or non-linear. Do you still remember the three conditions for linearity? Of course, you still remember. So the first condition is that what? The highest degree of any derivative must be unity. Is that okay? So the highest degree of any derivative terms must be unity. Secondly, there must be no sine, no cosine, or no tangent of the dependent variable. Clearly, in this particular equation, we don't have any sine, cosine, tangent. We don't have any logarithm function here of the dependent variable or even of the independent variable. So the second criteria is checked. Then the highest degree of the dependent variable must be 1. The highest degree of the dependent variable must be 1. Okay, there is no particular term containing the dependent variable standing alone. Okay, now the criteria that we are going to be working with to judge this particular case is the first criteria, that the highest degree of any derivative term present should be 1. And clearly you can see that the third derivative here has a power of 4, and even the first derivative here in dy dx has a power of 2. So we can see that because of these particular terms has actually not not satisfied the first criteria to check for linearity of a differential equation, then we can judge that this differential equation is not linear, simply because the derivative terms have powers other than 1. Is that okay? Okay, have powers or degrees. Take note, I'm gonna be using the words power and degree. Is that okay? So this is not linear. Is that okay? So this is for example 1. So let's check another example and see how this goes. So in example 2, the differential equation that we are giving is this. We have d squared y by dx squared all raised to the power of 2 is equal to x plus we have 4 dy by dx all squared raised to the power of 2 over 3. Okay, so we want to find, of course, the order, degree, the type, dependent variable, the independent variable, and the linearity of this differential equation. So let's dive in quickly. So beginning with the order. So the order of this particular differential equation is actually what? The highest position in terms of derivative. This is second order. So the highest derivative you can find, the highest derivative term that you can find here is the second order derivative term. So this is a second order differential equation. So let's go to the degree. So for the degree of this differential equation, remember you have to do what we did in the previous one, which is you have to actually take what? The third power of both sides. So when you take the third power of both sides, you have the 2y by the x squared. Remember there's already 2 here, but when you raise it to the power of 3, it becomes 6. Is that okay? So it's equal to x plus 4 dy dx all squared all raised to the power of 2. So this is the modified form of this differential equation. So having taken the fourth power of both sides, we can see now that the degree of this differential equation is 6th degree. Okay, so it's a 6th degree differential equation. Now let's check the type. Of course, the type is actually going to be ordinary differential equation. So there's no partial derivative parameter here, just normal ordinary differential parameter. That's the normal d operator. Then we have the next one, which is dependent variable. So the dependent variable, of course, is y, and the independent variable is x. Then finally we want to check the linearity. So is this differential equation linear? So to check if this differential equation is linear, of course, refer back to the criteria, which by now I believe should have committed to your memory. Then you test. Now looking at the terms in the differential equation, you can see that clearly it has violated the first criteria. Now take note, any criteria for linearity that is violated renders that differential equation non-linear automatically. So even if it's as little as one criteria that is violated, then that differential equation is no more linear. And clearly this one, we have in our derivative terms, we have a power of 6. So this is no more linear. In this particular first derivative term, you have a power of 2, so it's no more linear. Had it been they both had powers of 1, perhaps, and had it been this all squared was not here, then maybe it would have been linear. Is that okay? So it is not linear. Is that okay? So we'll still see more examples on linear and non-linear differential equations in another video, but for now I'm just going to give one more examples of a linear and a non-linear differential equation, so that we'll see how it is real life. Okay, because you're going to need to understand how to distinguish between linear and non-linear differential equations if you want to proceed in further understanding of this topic, ordinary differential equations. Okay guys, let's see some further examples. Alright, so for some further examples, I'm going to give us, let's see, for instance, I have a differential equation like this, the y by dx, okay, minus 2y sine x is equal to cos x. Assuming I had something like this, so and I ask you what kind of differential equation is this, so definitely you can be able to categorize this differential equation as linear, because any of those criteria, all of those criteria are satisfied we have the derivative term having a power of 1. Okay, derivative term has a power of 1. The dependent variable, which in this case is y, also have a power of 1, and of course there are no sines or cosines or tangents or logarithms of the dependent variable, so this particular one is linear. Is that okay? Now I now give you something else like this: d squared y by d by dx squared. Okay, then minus 2y squared cos y is equal to exponential 3x tan y. So I'm just coming up with something at random. Okay, now you see something like this and you want to check if this is actually linear or non-linear. So based on those three criteria, you can see that this particular term, the dependent variable, has a power of 2. Okay, and you can see in these particular terms here we have a cos y and a tan y. Is that okay? So we have cosine of the dependent variable and tangent of the dependent variable. Okay, so even if this particular first term satisfies the fact that it has a power of 1, this term over here and this term over here has satisfied the criteria that I stated earlier, so making this particular ordinary differential equation not linear. So that brings us to the end of this video. You should go through those criteria like I stated earlier in the beginning of this video and try to get your hand around more examples, and if there is any question you can leave it in the comment section, so I'll gladly attend to your questions. So thank you for watching. See you in the next video. So we're going to enter properly formation of differential equations. Alright, don't forget to like and subscribe and share to your friends. Okay, take care.